Hello everyone and welcome to this demonstration of our minor project. Our topic is preservation of historical documents through digital image enhancement. This project was developed by myself, Tithi Ghosh, along with my teammates Achishmita De and Ritusri Banerjee, under the guidance of Professor Sudipto Das from the Department of Computer Science and Engineering at Adamas University. Here is a quick overview of what we will cover today. We will start by defining the problem which historical documents face. Then I will outline the objective, then go through our methodology specifically focusing on the filtering and thresholding techniques we implemented. Finally, I will share our comparison result to show which methods works best. Let's start with the challenge. Millions of documents in archive, like government records and manuscript, are suffering from survey degradation like stains, ink bleeding, and fading that makes them unreadable for both humans and machines. Our goal is not just to scan them, but to digitally restore them. We aim to create a clean, binarized output that is perfect black text on a white background. Our core idea resolves around adaptive thresholding because, as we found, a single fixed setting simply does not work for every type of damage. Problem statement. This specific problem we are solving is the limitation of fixed values. Using the same crop size or threshold value for all images does not work well because each document is different. Real world documents are messy. They have uneven lightning, shadows, and faded ink. If you use a fixed global value, you lose data. Our project tests and calculates the optimal threshold value for each individual image to ensure no text is lost during the restoration. Objectives. We have three main objectives regarding this project, and they are grayscale conversion, that is to simplify the data by removing color to focus purely on light intensity. Noise removal for removing the stains and texture noise. And subject separation, where we use the adaptive thresholding to isolate the text from the background, creating the crisp digital copy. Methodology. Before we fix the images, we have to understand the damage. As we can see here, we default with various categories. Images with broken characters where ink has stripped away, then transparent images where ink blades through from the other side, and we can also see some high humidity wrinkles and significant aging spot for which filtering was required. Our methodology begins with the input image, which we immediately convert to grayscale to reduce the computational complexity. After then comes to the critical filtering stage. We did not just use one filter, we combined them. We used median filtering to remove salt and pepper noise, morphological operation to fix broken text structure, and homomorphic filtering to correct uneven lighting and shadows. After filtering, we move to the thresholding part. This converts the grayscale image into the binary. We focused on adaptive methods like Nick and Bretleroth rather than standard global methods to handle the local variation in the page. The final output image is a clean binarized document that is ready for digital archiving or OCR processing. Here is the visual flow of our system. You can see how the image moves from raw input through DPI standardization and grayscale conversion into our filtering block and finally through the thresholding logic to produce the output. Grayscale conversation. Let's look at the result. Here is our grayscale conversation. We used the standard formula 0.299R plus 0.587G plus 0.114B to strip the color while retaining the luminance information, which is important for distinguishing text. DPI conversation. We also implemented the DPI standardization. We resized the all image input images to 300 DPI. This is the industry standard for OCR and archiving. Homomorphic filtering. This slide demonstrates homomorphic filtering. You can see how the original image has uneven lighting where some parts are darker. This filter normalizes the brightness across the page so the text stands out evenly. Morphological filtering. We used erosion and deletion to remove small noises while thickening and reconnecting broken text strokes, making faint handwritten unreadable readable again. Median filtering. Here is a median filtering which is excellent for removing the salt and pepper noise. It smoothness the background without blurring the sharp edges of the text. Filtering summary. We analyzed which filter perform best for specific problem. As we can see in this summary table, morphological filtering was good for broken character, while homomorphic filtering excellent at fixed poor contrast and uneven lightening. Thresholding. Now the most important step, thresholding. We compared Nick, Savola and Bretley-Roth methods. We can in extensive tests using the different parameter values from 1.3 to 1.7 to find the value that balances noise removal with text preservation. Here is the comparison of the value 1.4. You can see the while Savola handles the background well, Niplek in the middle introduced too much noise, Bretley on the left is giving us a decent result but still has some artifacts. Now look at the result with a value 1.5. The Bretley-Roth method here on the left produces a very clean output with sharp text and minimal background noise. When we push the value to 1.7, we will notice that text start to degrade or become too thin. This confirms that higher values are not always better. Result. Our final analysis concludes that Bradley thresholding with a coefficient of 1.5 is the overall best method. It achieved a performance score of 87.81 out of 100 and PSNR of 78.26 dB. It was the most reliable across low contrast, moderate damage, and even severage damage categories. Literature review and the research gap. Our literature review identified key limitations in current research that our project aimed to solve. While existing studies analysis public dataset, there is a significant lack of diversity in region-specific and private archive. Similarly, standard OCR tools like Descartes platform poorly on degraded document without specialized preprocessing. We also found that while deep learning models were offer high quality, they are computationally expensive and data hungry, whereas the classical filtering methods used individually are often insufficient for complex damage. And these are the references of our project. Thank you.